All right, we are back with the next part of this little DSP thing where we've got an input wave format input wave signal where I basically said hello world. And we're going to bring that into Python here, and we're going to look at it in the time domain, then we're going to look at it in the frequency domain, and then we're going to maybe do some filtering and something kind of cool with it. And we'll see what that looks like. So right now, I did make some edits to the code from the previous example. I kind of cleaned things up a little bit. I just want to talk through those real quick. All of this still the same. And then I have my main function that I talked about. And we read in the wave file. And we show what the sampling frequency is. We look at what that data actually looks like. It's got it's got two channels, 0 and 1. We're just going to work with one channel. I just copy that over to I call it channel 1. The one thing that wasn't in the previous one is I just created the time axis or T axis. And that uses the NP arrange and the length of the data channel, and I divide it by the sample frequency. That gives us everything in time. And then I put the plots all into a one function because it's getting kind of clunky in the code having the plt dot title, plt.x label, plt.y label, and so on. Way simpler if I just go plot it. Here's the time axis. Here's the data I want plotted. And so we'll look at that. And then we jump right into the frequency domain. We run the FFT on the data from channel 1. We put that into this variable x. And you got to recall that the data in this array really is of the form of a complex number, so a plus bj or a plus bi, depending on what you do. And then we sort of repeat some of the similar things here. This is a little more spelled out than what I did up here, but really we're doing the same thing. Only we're doing it for frequency, and which takes one extra step. And we spelled it out here in steps. I kind of did everything on one line. You could do the same thing here. And then I took all the frequency plots and I put them into its own function so I could just drop the frequency axis, the frequency domain signal. And then as you recall, the frequency domain is a mirror of itself. We're sort of only concerned with the lower end of the frequencies since we're dealing with voice signals. Nobody speaks with super high frequency. Maybe some people are pretty high, but even that is not really all that high. And then, like I said, the time plot. These are just the different functions we threw it into. The time plot just does that. Added a little more clarity as to what it was, what it is. Frequency plots, we look at the whole thing, which looks like goalposts. It's a little hard to see the details. This enables us to see the details. I put a variable in there. Last time we were using 5,000. I just put the variable in there. That way, instead of using 5,000, we could use 500. We could use whatever variable we want. We just plug that into the function. So it's a little better, a little more reusable as code. And so let's just go run it so you can see. Here's the time signal. And because I put it, instead of using the discrete time or the discrete numbers in the x-axis, I actually converted it to units of seconds. So you can see this whole thing is over in basically less than 2.5 seconds before it just flattens out. And then we go into the frequency domain. Here's the whole thing. Because we were sampling it 44,100 hertz. Really, the best we can detect is half that value, and then the other half is the mirror of that. So really what we're interested in is all this action down here, which is super interesting and kind of crazy. And then we just go look at it here. We see the spike at right around 60, and then we see all these other various portions of the signal. And so it's kind of cool that way. And then here's the right side. It's the mirror image. So that's what's going on there. I think the code's just a little cleaner this way. So now we can kind of focus on some of the stuff that we really wanted to do here. Oh, that's right. There's one other little sneaky thing I did. Turns out when you do absolute value of x, that is not the same thing as np dot absolute value of x. These are two different functions. This is kind of a native Python one. This one is a part of the NumPy version. That actually turned out to matter. I had a heck of a time troubleshooting some stuff earlier. And so for that reason, you will actually see that code here, where now all of a sudden I've got np.apps. That's going to have to do when we get into this next part here, filtering. So I'll just delete that. And the next thing what we want to do is actually, let's build a filter. And when I first did this, I recorded probably two of these videos before I realized a huge mistake. Well, one was kind of like a really embarrassing one as I set up a filter. What I want to do is basically create a filter, and where I want to pass in the frequency axis and then the frequency domain signal, right? So our X that we've been working with. And what I want to do is some kind of filtering on that, and I was calling it a low pass filter because I was trying to get rid of a low frequency signal and keep all the rest. But in reality, if you suppress the lower frequency signals and keep everything else, what you actually have is a high pass filter. So I'm going to call it filter HP, and we're going to put in the frequency axis. We're going to have our X signal, and then we'll just have whatever the frequency is, F, that we want. Everything below it, we want to suppress it. Everything above it, we want to let it pass. So remember, we're in the good old US of A. We run, our power is 120 volts at 60 hertz. So I want to get that. We saw that little 60 hertz spike. We want to get rid of that. How do we do that? Well, we run it through a high pass filter. High pass is going to keep everything that's at a high frequency, and we're going to get rid of everything at a low frequency. So let me just take this and let's create a def of that. And of course, we want to be above 60, so let's just put it, let's say 75 is what we want. And I'm going to put this .0 here because I'm not totally sure if everything is going to be in a, if it's going to be an integer or if it's going to be some floating point, but that should help tell Python, hey, we're dealing with a floating point here, just try to be under that. And then I will want to make use of my frequency. Of course, when we're all done, we got to show off the work. Frequency axis. In this case, we won't use that. We'll use H. And instead of N, let's just stick with our 5,000. We could change that at any time. So then we'll just plot the result of what we do in this filter. Okay. So now we're just going to go define this function. We want to basically return a frequency domain signal where we filtered out the lower frequencies. So how do we do that? I'm going to do it probably in the most basic way I can think of doing it. Try to be as simple as possible, mostly for clarity and because maybe I don't know better. So I'm just going to define a variable I equals 0. I think this comes from one of my first programming languages that I learned was C. You always kind of had to declare your variables. And so we'll just say while I is less than length of the X signal that we're going to pass into it. We're just going to iterate through. So I equals, instead of I++, we'll do I1 plus I. I oftentimes forget that, and then I'm wondering why my code is stuck. Well, it gets stuck in an infinite loop because I'm never cycling through one. So in this case, we're going to cycle through everything, and we're going to start here for a second. And then the next thing I want to do is I want to actually create the function, or the array that I'm going to convert, that we're going to allow. That we're going to basically take x. It's got all these complex numbers in it. We're going to suppress the ones that are in the lower frequency ranges, and we're going to pass the ones that are in the higher frequency. So that's our high pass filter. And so in here, what we got to do is check. So we're going to check everything. So if the frequency axis number is less than our frequency that we care about. So if we're in this case, I think we're going to start with what did I say? I felt like I said 75. So if we are at a frequency less than 75, we want to suppress that. So I'm just going to say suppress. Else, otherwise we're just going to let it pass. So pass, although we're not going to say pass. That's something we could do. Really what we're going to do is go h dot append x of I. So we'll always wants to do some crazy stuff. So okay, so if we're above 75 hertz, pass that sucker on through. If we're below 70 hertz, we need to suppress that. So how do we suppress that? I'm going to use probably a terrible technique, but we'll use it anyways. H dot append. So we're just going to append what we do to x. So x of I, except now we're just going to divide it by the absolute value of x of I. So basically we're just going to we're going to divide it by the absolute value of itself. So that should just send everything to 1. So we're going to send this whole thing to 1. And you recall when we were looking at those frequency plots, we were in numbers of like e to the 12th, right? So super large. So if I send it to 1, that's e to the 0. That's absolutely going to suppress everything, and we should just see a straight line here. There should be no frequency signal at that point. Okay, and now I've already, we think we're good to go here, except we're not. One last thing we need to do. Hopefully we're going to exit out of this while loop. We're going to iterate through everything. It's operating an O of n, and we're just going to return h. Okay, so that should meet everything we need. And usually what I do is I get super excited. I'm like, oh man, I think I figured it out. Let's just fire away, and we'll just see if it blows up on me. Here's our time domain. Here's the frequency domain earlier. Like I said, e to the 12. Here's the left side of it. Here's the right side of it. And then now we should be looking at the filtered version of it. And it's a little hard to see anything. It doesn't look any different than what we just saw. But now when we zoom in on the left side, we see it is totally suppressed. We no longer have that 60 hertz spike there. And then you're going to be like, oh, cool, okay. And then we go, oh, crap. There it is hanging out in the reflection. So we did not do a great job of filtering this because we did not handle the upper end. We did not handle the reflection of this signal in the frequency domain. So we need to go figure that out. So we need to go edit the code. Number of ways we can go do that. I'm going to, like I said, I'm going to try to do it as probably in the worst way possible, but mostly for clarity. So I'm going to do this little cheater move where I'm just going to create a count. I'm going to set that equal to 0. And then every time I do this, I'm just going to count. CNT equals 1 plus CNT. Why did I do that? Well, I did that because I want to come back down here and do like a simple for loop for k in, or actually I'll just do a while. You know what we'll set I equal to 0 again. And we'll say while I is less than CNT, which is our count. So while we're less than our count, all I'm going to do is take h of So I'm going to take all the ones at the far end of it. So the length of H minus I. So right now I is 0, so I'm going to subtract off the total. So I'm going to start at the very end of it. So the last thing of H is going to basically equal, and I'm going to do the same thing I did up here. Except I'm not going to do append. I'm just going to set it equal to basically H of length of H minus I divided by the absolute value of, again, that length of H oops, absolute value of H. Oops, sorry. Oh, we're getting confused already. This is why it's not good. All right, so this position of H is going to be that divided by the absolute value of basically that number. So H, that, and it should be exactly this. Let's try not to think too hard here. It's difficult doing math in public. Okay, now this is great, except it'll run to infinity because I haven't updated I. I equals 1 plus I. Okay. So we should be operating on the back end on the very last number. So each time we're going to actually decrement from the total the last point in H all the way till we get to the count, which should be here, which we determined here. So if we've done that right, we'll actually see a mirror of our H signal. So let's fire away on that. Here's our time signal. Here is our original signal in the frequency domain, and we notice the spike here at 60, and we notice the noise down here, and we notice the same thing over here on the higher end, on the reflection. And now, we blew up. That's neat. Now we got to go figure out why we blew up. Let's see, what is it saying? Index error. Oh, we're out of range. So usually when we're out of range, we have an OBOB error and off by 1. So when we're subtracting that, so really all we got to do, now we just got to throw in these -1s. Or if I don't want to throw in the -1, I could throw in the -1 here. Let's actually, maybe this is just a good exercise in being silly. And look at all this typing I'm doing, and then we can run it, and now we'll be okay. Time domain, frequency, here we are. Okay, so now it actually worked. These things look like reflections. Now we see the 60 hertz spike gone, everything's flat. And if we've done it right, the next one should be the opposite of that, and we've got it flattened out there. Okay, cool. So we've kind of accomplished what we wanted to do there. I'm going to come back to this silliness where I did the -1. I could have just set this to 1 and gotten rid of these -1s, which I think I will do because I think that's just cleaner. If you program at all, you'll run into that error. Happens all the time. Or maybe it doesn't if you're really good at coding. If you're moderately good at coding, you won't make the mistakes I make. There we are. We'll run through it again. Looking good. Gone. So now we've got this high pass filter. All the higher frequencies have been filtered, or have all the lower frequencies that we said have been filtered. All the higher ones have been passed through. So thus we got a high pass filter So we've successfully made a super crude high pass filter. So I'm going to stop it there.